we know that if two vectors are orthogonal, then their dot product is 0. And it means that they're perpendicular if you're in R2 and R3. Higher than that, all it means is the determinant, or not the determinant, the dot product is 0. If you have an orthogonal set, then we mean that each vector in the set is orthogonal to every other vector in the set. So we want to check this set of vectors. Let's call this U, V, and W. In order to check to see if this is an orthogonal set, we need to find the dot product of every pair of vectors possible. So we need the dot product U and V. We need the dot product U and W. And we need the dot product V and W. Okay, and you can tell if there's a lot of vectors in your set, it's going to be hard to take all these dot products. But this is not too bad. So dot product U and V, so I get 0, -2, +2. And that is 0. U and W, I get -5, +4, and +1. That's also 0. And then V dot W, 0, -2, +2. That's also 0. So it all checks out. We have, every vector is orthogonal to every other vector. So this is an orthogonal set. If we have an orthonormal set, that means that it's orthogonal and they're unit vectors. So orthonormal sounds like a made-up word. I guess it is. I guess it is a made-up word. Orthonormal means an orthogonal set of unit vectors. So if we want to convert this into an orthonormal set, we just need to normalize the vectors or turn them into unit vectors. So let's find the magnitudes of each vector. So magnitude of U, the square root of 1 squared plus -2 squared plus 1 squared. So that's 1 plus 4 plus 1. So that's square root of 6. So let's call this U normal. U normal would be 1 over root 6 times our vector U. I messed up there. 1, -2, 1, which of course would be 1 over root 6, -2 over root 6, 1 over root 6. All right, let's do magnitude of V. So we get square root of 0 plus 1 squared plus 2 squared. That's square root of 5. So we'll call this Vn would be 0, 1 over root 5, 2 over root 5. And lastly, let's do the magnitude of W. Square root of -5 squared plus -2 squared plus 1 squared. So that's 25 plus 4 plus 1. That's a square root of 30. That doesn't reduce either. So we'll call Wn. We're going to divide W by square root of 30. So -5 over root 30, -2 over root 30, and 1 over root 30. So now we would say the set that's UN, Vn, and Wn, that is an orthonormal set. Okay. They're orthogonal. They're still orthogonal, but now they're unit vectors. Okay. So now let's talk about projections. So a projection is like a shadow. You've got a line, which is the span of a vector, say u. So we got vector u, we span that one vector, we get a line. We have this vector y, we want to project y onto that line. So what that means is, so if you had a light that was shining light rays perpendicular to the line, then this vector y hat would be the shadow cast by y onto the line, right? So you could imagine, the light would hit the line and it would create a shadow here. Okay, so the shadow is what we call the projection. So we have a formula here. Let's talk about this for a second. So if we look at a vector that's orthogonal to u and orthogonal to this line, such that when we add that vector to the projection, we get y. So we call this vector z. So z is y minus y hat, or you could say y is y hat plus z. Okay, so z is orthogonal to u and orthogonal to y hat. And y is the sum of those two vectors. So if I picked this vector up and placed it here, right, you see it's just the parallelogram rule, right? So y is the diagonal of that parallelogram. Okay. Well, y is in the span of u. So y is some multiple of u. It's some constant times u. So we're going to call it, let's call it alpha u. So it's some multiple of u that, it's somewhere on the line, okay? And next, we're going to take the dot product of u on both sides of this equation. So we're going to dot product, this is a vector. We're just going to dot product u times that vector, and we're going to dot product u times y. And you can distribute dot products. So this would be alpha u dotted with itself plus z dot product with u. Alpha is a constant, okay? Alpha is the multiple that scales u out to y hat, to this shadow. All right, well, since u and z are orthogonal, we know that this dot product is 0. Okay. And now if I just divide both sides by u dotted with itself, I get this constant. So I get the constant alpha by making this calculation. So in my formula here, in my dot product, not dot product, in my projection formula, that y hat has to be alpha times u, I'm just going to replace alpha with y dot u over u dot u. So we get this formula, the projection of y onto the line L, right? We're calling this line L. It's alpha times u, and alpha is this y dot u over u dot u. Okay, so let's do an example. I've got y and u. It says find the orthogonal projection of y onto u, then write y as the sum of two orthogonal vectors, one in the span of u and one orthogonal to u. Okay, so write y as the sum of two orthogonal vectors. So that is this. This is y written as the sum of two orthogonal vectors. Y hat is this guy, and z is orthogonal to that, right? And y hat is the vector that's in the span of u, and z is the one that's orthogonal. Right? So when it says right y is the sum of two orthogonal vectors, one in the span of u, that means that's the projection. And the one orthogonal to u, that's what we call z, which is y minus y hat. All right, so let's find the projection first. So this is going to be y dot u over u dot u times u. Okay, right, so this guy is going to be a scalar, and we're going to multiply this times u. So what's y dot product with u? So we get 28 plus 12. 28 plus 12 is 40. U dotted with itself. So it'd be 4 times 4 is 16. 2 times 2 is 4. So 16 plus 4 would be 20. So this reduces to just 2. 40 divided by 20. So when we multiply these, we get 8 and 4. So 8, 4 is the projection. So now we need to find the vector orthogonal. So z is just y minus y hat. The vector y minus the orthogonal projection. So that gives us negative 1, 2. All right, so we're getting z by using y and y hat. So how do we know that z is correct? You could have messed up y hat, right? So you check by making sure that z is orthogonal to u, right? So take your original u vector. Let's find the dot product of z and u. If it's orthogonal and it adds up to give us that projection, then we know that this is correct. So I'm just going to check this. So z, it helps to write it down correctly. Z dot product with u. So I get negative 4 plus 4. That is indeed 0. So this z is correct. So now y is equal to y hat plus c. So the first part says find the orthogonal projection of y onto u. That's this vector. And then it says write y as a sum of two orthogonal vectors, one in the span and one orthogonal. That's this one here. All right, so this one is similar, but it says compute the distance from y to the line going through u in the origin. Okay, so let's go back to our picture. Let me clean it up here. We want to know the distance from y to the line. So that means the endpoint to the line here. And if we just look at this, we can see that that's going to be exactly the same as the magnitude of z, right? So what we need to do is to find the magnitude of z. So we've got to find the projection, and then we have to find z with that projection. And then we need to find the magnitude of z, and we'll know how far y is from the line. Okay, so let's do the projection first. So y hat is y dot u over u dot u times u. We switch colors. So y dot u, so it'd be 24 plus 6. So that's 30. And then u dot u, that would be 8 times 8 is 64. 6 times 6 is 36. 64 and 36 is 100. So we get 3/10. So that'll be 24 tenths and 18 tenths, which we can reduce. That is 12 fifths and 9 fifths. All right, so that's our projection. So now we need to find z. Z is y minus the projection. So y is 3, 1. We're going to subtract the projection. All right, so let's change y so that it's a fraction over 5. So we'll call this 15 over 5, and this is 5 over 5. Okay, 15 minus 12 is 3 fifths. 5 minus 9 would be negative 4 fifths. So that's z. And we're not done. We have to find the distance. The distance is going to be the magnitude of z. So square root of z dotted with itself, or the square root of the sum of the squares of the components. So this is 9 over 25 plus 16 over 25. Is that 25 over 25? We get 1. Square root of 1. So this y is only a distance 1 away from that line.